In the last lesson, we learned one method to analyze circuits containing capacitors and inductors using their models, which are differential equations. In this lesson, we will study the frequency analysis. This is a simpler method that provides a clearer understanding of how circuits with capacitors and inductors behave. Before we start, it is important to understand the concepts of time domain and frequency domain. In this course, we explore the RC and RLC circuits. We learn their behaviors. For instance, the RLC circuit can oscillate at a specific frequency and shows damping. We derive differential equations to capture the behavior over time. Similarly, with the RC circuit, we have a differential equation that accurately describes its response when exposed to a pulsating signal, as shown in this simulation. We understand the behavior of these two circuits in time domain. The simulation tells us what happens at every time point of the simulation. But that is not the only way that we can see the behavior of a circuit. In frequency domain, we analyze how the circuit behaves for each frequency. When we studied the RC circuit used as a filter, we learned that the filter is capable of removing frequencies from the original sound. Like in this audio example, we can hear that in the beginning the sound is bright and then it gradually becomes darker and quiet. The frequency analysis can help us understand how the filter affects each frequency of the input signal. Let's start by making a few simulations. Here you can see in blue the input signal and in orange the output signal of the filter. At low frequencies, in this case 1 Hz, the output almost overlaps perfectly with the input. But as I increase the frequency, notice that the time scale in the plot is changing. The output signal starts getting attenuated. At the same time, the sine wave is being shifted. We can see that this filter affects the amplitude of each frequency differently, and it also affects the phase, which is the position of the sine wave. We could go frequency by frequency and make a note of the attenuation and phase, and that will give us the frequency domain behavior of the filter. If we made such a plot with information about the magnitude and phase for each frequency, we will get what is called a Bode plot. Here we can clearly see that this is a low-pass filter, in which any frequency above certain value starts getting attenuated more and more and more. In the bottom we can see the phase, which starts unaffected, but gradually moves until there is a 90 degrees shift. There is an issue with the Bode plot. It only works if the input signal is a sine wave. If we use any other kind of waveform, like a square, the result can be misleading. But we have another tool that can help us understand how the filter will respond to a more complex waveform. It is called the Fourier transform. In simple terms, using the Fourier transform, we can convert any complex signal into a group of sine waves of different frequencies. For example, a square wave can be created by summing many sine waves of specific amplitudes. Each sine wave is called a harmonic, and in this plot we can see how the wave looks more and more like a square as I increase the number of harmonics. We're not going to cover Fourier transform in this course, but I just wanted you to know it exists and that it is a useful tool. Now we will learn a simpler method to analyze a circuit directly in frequency domain. We will use the Laplace transform. Even when the name sounds complex, using the Laplace transform to analyze a circuit is easy, especially using the Wolfram language. In this table you can see the two basic formulas that you need to remember. This method is simple. When analyzing a circuit, when we see a capacitor, we replace it with a resistor that has the following value: 1 over S times the capacitance value. The S is a symbol. We don't put any value yet. When you find an inductor, you have to replace it with a resistor of the value S times the inductance. We will see next an example of how a circuit is analyzed using this method. Let's see how we will analyze the circuit using the Laplace transform. The circuit is simple and consists of two components connected in series. In the bottom diagram you can see the RC circuit, while in the top you can see a circuit that has the same topology, but instead of a capacitor, it has a resistor. So the diagram above is a voltage divider, and below is the RC circuit. To analyze the RC circuit using the Laplace transform, the first step will be to change the capacitor by a resistor of value 1 over SC. By doing that change, we end up with a voltage divider, so the circuit in the top, for which we already know the formula, which is the input voltage V1 times R2 over R1 plus R2. We will replace the value of R2 by the new capacitor value, 1 over S times C1. Now the formula is in frequency domain, and we made that explicit by adding the S, so we know that the voltages are in function of S instead of time. S will represent the frequency domain. We can simplify the formula using the Wolfram language, and we can write it as follows. Notice that the term V1 of S is now in the denominator of VC1S. When written this way, it is called a transfer function. The formula is telling us what's the relation between the output and the input of a circuit. And now that we have a transfer function, let's figure out what we can do with it. Here is the transfer function we obtained before. I'm going to put numeric values for the resistor and capacitor. The capacitor will be 10 microfarads and the resistor 1 kilo ohm. And after simplification, the only symbol in the transfer function is S. We can use the function transfer function model to convert the formula into a Wolfram language transfer function. Then we can use the function Bode plot to show the frequency behavior of the circuit. We have already seen this plot. The RC circuit is a low-pass filter. Instead of creating the Bode plot, we can manually obtain the magnitude and phase of the output for a given input frequency. To do that, we can replace the symbol S by omega times I. Omega is the frequency of the input signal in radians per second, and I is the imaginary number. If we want to work in hertz, we need to use 2 pi fi. Here's an example. If I want to show the behavior at 100 Hz, I replace S by 2 times pi times 100 Hz times I. The result is an imaginary number. To get the amplitude of the signal, we can use the abs function. The result number is the amplitude of the output sine if the input is a signal of 100 Hz of 1 volt. To get the phase, we use the arc function. This is the phase shift of the output in radians. Another interesting thing is that we can easily convert the transfer function back and forth from differential equations. For example, if we reorganize the transfer function by moving the denominator to the other side and expanding all the terms, we can write it in such a way where only the term VC1S has the symbol S. Then we can replace the symbol S by the time derivative, and we have the equation back to time domain. Let's make another example. We will analyze the RLC circuit we saw before, but now directly in time domain. In this circuit, we are interested in the current. In order to calculate it, we need to get first the equivalent impedance of the three components, R, C, and L. Since they are in series, we can add all the impedances, but first, we need to convert the capacitor and inductor to frequency domain. For that, we replace the capacitor by 1 over SC1 and the inductor by SL. Here you can see the equation of the equivalent impedance. To calculate the current, we divide the input voltage by the impedance, and after simplification, we obtain the following transfer function. At this point, we can evaluate it as we did for the RC circuit or create a Bode plot. This example uses the formulas we obtained for the values of the inductor and capacitor based on the damping and natural frequency. It replaces them into the transfer function, then it shows the Bode plot. We can see how the natural frequency and damping affect the Bode plot. We have a kind of bandpass filter where the low and high frequencies are attenuated. The frequencies around the natural frequency receive less attenuation. We can control how wide or narrow this band is by using the damping parameter. Sometimes, obtaining the transfer function of very complex circuit is a complicated task. When the circuit is created in System Modeler, we have an alternative approach using the function to obtain linearized models. In this example, I have created a version of the RC circuit which has one input and one output. We can use the function system model linearize, and that will return a state space model. A state space model is simply a different representation to capture the differential equations. We can easily convert this representation to a transfer function. We can use either the transfer function or the state space representation to create the Bode plot. And we can even run simulations directly in this representation. As a summary for this lesson, the frequency analysis shows how a system responds to each frequency. We can obtain frequency models using the Laplace transform. Capacitors and inductors are replaced by their frequency domain equivalents, 1 over SC and SL. Once we have replaced the models, we can use any analysis to solve the circuit and obtain transfer functions. With the transfer function, we can create, for example, Bode plots. And last, the function system model linearize simplifies obtaining frequency models.